One of the first things we do after the orbiter returns from a mission is remove the Space Shuttle main engines so that they may begin the refurbishment process. The yellow piece of equipment that you see here is the modified heister that we use to remove the main engines from the orbiter. Removing engines is a very slow and methodical process of ensuring everything is lined up correctly as the engines are removed from the aft compartment. Each engine is 14 feet long and 7.5 feet wide, providing 375,000 pounds of thrust during liftoff. As each engine is removed, it is transported to the engine shop located next to Orbiter Processing Facility Number 3. Engineers and technicians then refurbish the engines in preparation for their next use. During the STS-133 processing flow, the right orbiter maneuvering system, or OMS pod, was removed from Discovery to address the failed helium isolation valve issue from the previous mission. The pod was lifted to the transfer aisle prior to being transported to the hypergolic maintenance facility here at Kennedy Space Center for servicing and maintenance. On May 11th, the external tank 137 arrived by barge from the Michoud Assembly Facility in Louisiana. The barge, named Pegasus, is 200 feet long and 35 feet wide and was built specifically for transporting the external tank. Within the confines of the turn basin, a commercial tug carefully assists Pegasus as it maneuvers up to the dock. The external tank inside Pegasus is 154 feet long, 27.5 feet in diameter, and holds over 500,000 gallons of propellant. The tank weighs over 58,000 pounds empty. Once on dock, we use the external tank transporter to move the tank off the barge and over to the vehicle assembly building. While the entire offload process takes technicians and engineers approximately 2 hours, the actual travel time is only 10 minutes for the quarter-mile trip. Although the external tank looks like one extremely large tank, it is actually made up of 2 internal tanks. The liquid oxygen tank is at the top or pointed end, and the liquid hydrogen tank is at the bottom. The function of the external tank is to provide liquid hydrogen and liquid oxygen to the 3 Space Shuttle main engines. The aft bipod struts and propellant feed lines you see here connect to the orbiter. The outside of the external tank is covered in a polyurethane foam that protects it from extreme temperature variations seen during flight. Back in the orbiter processing facility, Discovery's midbody is closed out in preparation for rollover. The yellow strongbacks you see here assist the payload bay doors to close in the gravity environment of Earth. The KU-band antenna is used to transmit and receive video and data communications with the ground. The payload bay doors will be reopened again at the pad for payload installation. After spending 119 days in the orbiter processing facility, completing all required maintenance, testing, and checkout, Discovery is now ready to move to the vehicle assembly building, where it will be mated to the external tank and solid rocket boosters. Similar to the tank transporter we saw earlier, the orbiter has a unique transporter as well. The Orbiter Transport System, or OTS, has 76 wheels on 19 axles and was built specifically for the orbiter. Once Discovery is safely in the vehicle assembly building, we begin the process of lifting the orbiter off the transporter and joining it with the external tank and solid rocket boosters. Discovery is secured to the transporter using the same attach points that will eventually connect it to the external tank. There are 2 structural connections in the aft and 1 in the forward. A sling is connected to the orbiter so that cranes can lift Discovery and move it into the vertical position. Lifting the 200,000-pound orbiter requires use of a 350-ton crane and a 250-ton crane. Once Discovery is hanging in the vertical position, the smaller of the 2 cranes is disconnected, and the larger crane lifts the orbiter up and over the transom into the integration cell. It takes approximately 12 hours to lift the orbiter and get it into the mate position. Technicians closely monitor the movement of the orbiter and are in radio contact with the crane operators at all times. Once in place, the orbiter is bolted to the external tank and the sling is removed. Now that the orbiter has been mated, we are ready to move the complete shuttle stack out to the launch pad. The stack is moved by a crawler transporter which weighs 6 million pounds and uses 150 gallons of diesel fuel per mile. A unique viewing opportunity was provided to Kennedy Space Center personnel for the evening of rollout. Employees could bring family and friends out to the turn basin to enjoy the beautiful view as the STS-133 stack slowly made its way to the launch pad. Instead of wheels, the crawler transporter has 8 tracks with 57 cleats per track. Each cleat weighs 1 ton. At a speed of less than 1 mile per hour, it normally takes approximately 8 hours to travel just over 3 miles from the vehicle assembly building to launch pad 39A. Discovery arrived at the launch pad on the morning of September 21st. Once at the launch pad, we spent about a month doing a full system checkout of the tank, boosters, and orbiter in preparation for launch. Here you see the STS-133 primary payload, the Permanent Multipurpose Module, or PMM, carefully being installed into Discovery's payload bay. Following final closeout inspections of the installed payloads, the payload bay doors are closed for flight. The STS-133 crew joined the Kennedy Space Center launch team for the Terminal Countdown Demonstration Test, or TCDT, in mid-October. TCDT is a full dress rehearsal of the final hours of launch countdown and provides key training for both the flight crew and the launch team. The flight crew checks the fit of their spacesuits, practices emergency evacuation procedures at the launch pad, and inspects their mission cargo in the shuttle's payload bay. This training allows them to familiarize themselves with the vehicle and become acclimated with safety equipment and procedures. Astronaut support personnel representatives assist the crew during the TCDT operations.
I agree.
On the morning of November 5th, launch countdown was scrubbed due to a leak at the ground umbilical carrier plate, or GUP, interface on the external tank. The GUP is located at the end of the gaseous hydrogen vent arm on the fixed service structure of the launch pad. During scrub turnaround operations, a foam crack was also found on the liquid oxygen interface flange of the tank. Both the GUP leak and the foam crack would require substantial investigation and evaluation by the Space Shuttle program over the coming weeks. The GUP plate holds a large diameter pipe that collects excess hydrogen gas from the tank as it is being filled with liquid hydrogen. The venting system funnels the gas to a larger pipe that then takes the hydrogen gas down the fixed service structure of the launch pad and out to a flare stack that safely burns off the excess hydrogen. At liftoff, the GUP retracts away from the tank, cutting off this connection. The vent arm pulls back to the tower and safely away from the shuttle. Because the GUP's connection to the tank is so important, it has sensors in place to watch for leaking hydrogen. Launch controllers track these readings closely, and if any of these readings are outside the allowable limits, the countdown is halted. After discovering the GUP leak during countdown, the external tank was drained of its liquid hydrogen and liquid oxygen and cleared of excess hydrogen gas. At that point, it was safe for technicians to begin collecting data to better understand and analyze the leak. An investigation team was formed to fully evaluate the hardware configuration, installation, and functionality and determine if any modifications would be necessary. Teams performed an initial inspection of the flight seal and quick disconnect prior to sending them to the lab for extensive micro-level inspections. As part of the investigative effort, the complete ground umbilical carrier assembly and vent line was disassembled and inspected. The same repair is performed on the other crack stringers found at the launch pad. In addition, a radius block modification was also performed on the inner tank stringers. The radius block modification provides additional structural support in areas known to carry much of the structural load of the external tank. These radius block essentially fit over existing stringer edges through which securing rivets are installed to provide additional structural support. Once all repairs were made to the external tank, the stack was again placed atop the crawler transporter and carefully rolled out to Launch Pad 39A on January 31st. Brilliant xenon lights illuminated the vehicle, creating a spectacular view for everyone present. To verify the integrity of these repairs, an instrumented tanking test was performed on December 17th. Numerous strain gauges and temperature sensors were installed to record data from the tank as it chills and warms again during the loading and offloading of propellants. Following the completion of the instrumented tanking test, we rolled the shuttle stack back to the vehicle assembly building for further non-destructive evaluation, or X-rays, of the external tank stringers that were not accessible at the launch pad. Rollback occurred on December 22nd, and engineers immediately began inspecting and evaluating the external tank. X-rays revealed an additional 4 small cracks on 3 stringers. These stringers would require the same repair as performed on the other cracked stringers found at the launch pad. In addition, a radius block modification was also performed on the inner tank stringers. The radius block modification provides additional structural support in areas known to carry much of the structural load of the external tank. These radius blocks essentially fit over existing stringer edges through which securing rivets are installed to provide additional structural support. Once all repairs were made to the external tank, the stack was again placed atop the crawler transporter and carefully rolled out to Launch Pad 39A on January 31st. Brilliant xenon lights illuminated the vehicle, creating a spectacular view for everyone present. Once back at the launch pad, a full system checkout of the tank, boosters, and orbiter was completed in preparation for launch. STS-133 is the 133rd Space Shuttle mission and Discovery's 39th and final mission.
Yeah, we're going to compress about 18 months of work into about 5.5 minutes. All right, this is a C-5A military aircraft. It delivered Express Logistics Carrier 4 to us from the Goddard Space Flight Center back in mid-August of '09. The Goddard team, under the direction of Kevin Carmack, put the ELC carrier together, and then we here at KSC with our Boeing colleagues finished the outfitting of that element. The permanent multipurpose module Leonardo returned on the 19A STS-131 mission back in April of last year, and it returned to our building on the 26th of April, where we pulled all of the cargo out from that last flight and started the modification process to get it ready to become the PMM. That work was performed predominantly by our Italian colleagues from Thales Alenia Space under the direction of Roberto Barratt. They did a wonderful job, and by the end of July they had the element converted to a PMM. During our processing flow, we perform a number of tasks to get the module ready to go fly. This will be the 8th flight of Leonardo, and in this scene you can see a simulator of the docking mechanism on the station that we made up to the docking mechanism on the module every flight to ensure that it's going to seal properly against the station. This time for final assembly and installation onto the station. Here's ELC-4 being moved over to our element rotation stand. We did that periodically throughout the floor, as there's a top surface and a bottom surface on that element, and we need to be able to flip it over like a pancake. And once the internal modifications were completed in early July, the external mods continued on for a while. We started our rack installation process. We have 14 racks flying up with us in the module and carrying up a total of 8,500 pounds of cargo. The external mods continued in parallel with that, and this is a view of some of the Thales Alenia Space personnel installing some of the modified blankets and shielding on the exterior of the vehicle. These new shields were installed to help the vehicle survive the 10 years it's going to see in space. The very large ORU flying on ELC-4, the one and only, is a thermal radiator for the exterior of the station. We hope we never have to use it, but we'll have it pre-deployed there if necessary, and that's a shot in August of us installing that. Once ELC-4 was completed, we lifted it up and mated it to its keel assembly. It uses this keel assembly when it's installed in the orbiter to survive ascent loads. The keel does stay behind when the element is deployed to the station, and will be one of the few things that will return home in Discovery's payload bay. After that, the element was weighed and installed into our transportation canister. Robonaut 2. R2 arrived at KSC in early August and went through about a week of post-delivery checkout and preparation activities. In the end, after they checked out all of the operations of the robot, we packaged it up into its launch enclosure and installed that launch enclosure into the module for flight. In early October, on the 5th, the element was lifted out of its work stand for the last time. We weighed it, calculated its center of gravity, and then moved it over into our transportation canister. In this view, you can see it being lowered down onto the load cells that are used to actually measure the weight of the element. The ELC-4 element had been installed in the canister just prior to this, so the PMM was the second and last element to go into the canister. The plastic you see there draped over the docking mechanism is intended to protect us from some minor contamination that we might see during our transport out to the pad. Was removed during our final closeout operations out at Pad A. Once both elements are in the canister and the doors are closed, it's moved over to our canister rotation facility, where it's tilted up on end atop the transportation mobile transporter that we use. And on the 7th of October, my wedding anniversary, we delivered both elements in the canister out to the pad. We usually do this in the middle of the night to avoid traffic and because the weather is generally better for us. It takes about 4 hours to get there, very slowly and very carefully. Once up on the pad surface, we hoist the canister up into the rotating service structure, which you can see has been pulled back away from the orbiter. Inside the rotating service structure, there's a large gantry called the Payload ground handling mechanism that can actually reach in and extract the payload elements from the canister. The canister can then be lowered and taken away. The RSS is rotated around the orbiter, and the elements are installed by that ground handling mechanism into the orbiter. Once we made all the appropriate electrical connections and did our final closeouts, hey look, that's me. We performed our final closeouts out at the pad, and on the 16th of October, we closed the payload bay doors for flight. Again, that was quite some time ago, but I'll never forget that day. A lot of us like to go out and watch that because that's our last opportunity to basically blow our hardware a kiss goodbye. And that's where we've set ever since. Again, we've gone a few miles horizontally, and hopefully today we'll go a few miles vertically and get these two elements in space and attached to the International Space Station where they belong.
It's quite a lot of work, quite a lot of detailed work to get the payloads ready to go fly into space.
Absolutely. It's a team effort with great folks all around the United States and all around the world for that matter. We spent a lot of time on this mission in particular working with our colleagues from Italy, and that's been an absolutely wonderful experience.
Absolutely. Well, we also have another tape that we wanted to play in which you sort of give us a tour of the permanent multi-purpose module. We look forward to taking a look inside.
All right, great.
The permanent multi-purpose module, once again, is a modified version of the Leonardo multi-purpose logistics module that flew in space 7 times, I believe, and carrying hardware to and from space. And in this case, it's been modified to become a permanent module that will not come back to Earth.
Right. This module is going to serve as that extra closet or extra garage bay that you always wish you had. You know, the station's growing and the cargo on board is taking up a lot of space, so we just need some more places to stash things, and the PMM will provide us some very much needed space. So this is a view looking in the hatchway, and I think next we're going to proceed on inside. This was taken during our final phases of our closeout activities, so all of the cargo at this point is on board. The great big white box you see in the back in that original image was Robonaut 2 packaged up in his enclosure, and you can see him there on the far right hand side of the screen right there. A lot of cargo items are they're large and oversized, so they're in special containers that we strap into place, and you can see that they're covered in foam for protection. We have an extra treadmill that we're carrying up, some spare parts for the thermal control system for the station, food, all manners of things that the crew needs to live and work in space. Again, 8,500 pounds of cargo. Some of that cargo is going to be used right away. Some of it's going to be used later on over the station's lifetime. And certainly much of this volume inside this module will be filled up with additional cargo items once the element gets on orbit and attached to the station. There are a few empty rack bays. We don't have enough performance to carry up a full module on this flight, so those empty rack bays will again be filled with cargo later on. And here's Robonaut 2 again running through his paces. He's an absolutely amazing device. He will teach us a lot about how robots can help us in space, both inside the station and ultimately outside the station. And perhaps one day we'll be able to use robots that can trace their lineage back to Robonaut to do some of the more dangerous and maybe mundane things in orbit so that the crew can be freed up and protected from those things. Leonardo is basically a very low mileage used spacecraft, the way we look at it. He's flown for about 90 days in space and cumulative time, and has traveled, I think, 40 million miles in total so far. But over the 10 years that we expect the module to stay in space attached to the space station, we have calculated that roughly it will travel about 10 billion miles. And so it's got a lot of good miles left in it. We're sad to see Leonardo go. He's been part of our family for over a decade, but we're all excited to see him put to good use as a permanent addition to the space station as opposed to ending up in a museum somewhere.
Absolutely.